Okay, I may as well just keep going here. We're looking at 6.5, the next section, double angle identities. This is the last section in chapter 6. So ideally, we're going to be able to look at some of these proofs or some of these equations and simplify them using a variety of different identities, this being the last ones that we're going to show you. Okay, so these are called double angle identities, and they look like this: sine 2a, right? So it could be, say, sine 2x or whatever. That's basically, it's a little bit different than 2 sine a is not equal to sine 2a, right? Or 2a. This is the same as saying sine a plus a, if you like, right? So that's what this ends up looking like. And if you look at sine a plus a, let's see how we can derive this, right? So sine a plus a, let's just make that sine a plus a. So that would be sine a cos a plus cos a sine a. Since multiplication doesn't matter, this becomes 2 sine a cos a. All right, and that's actually an identity. And it just so happens that that works with these other ones as well. Cos a plus a, blah, 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 boom, there you go. Okay, you're going to have cos squared because you're going to end up with, let's look at cos a, right? It's going to be cos, sine, sine. So it's going to be cos a, sine a, cos squared, sine squared. Boom, there you go. Now from this, though, you got to remember that you have other identities as well. Do not forget your Pythagorean identities, right? Where if I want to write something with cos squared, right? Cos squared is 1 minus sine squared, and sine squared is 1 minus cos squared. So if you sub 1 minus sine squared in here, right, you end up with actually this one down here. And if you sub in 1 minus cos squared in for this, you end up with this one here. All right, so these are easily derived from our sum and difference formulas, right? A plus A or an A plus A. And then from this here, we can use a Pythagorean identity to explain these other two versions. All right. Now, I don't have a fancy way of showing you the tan one, except it's still going to be the same thing, right? But the tan one, we all know, is significantly less pretty. So if you sub the numbers in there and try them yourself, you'll end up with that, and I'm just going to leave it at that, okay? Because we have other things that we need to do. So let's look at a couple of things here. Let's look at our identities. So cos 2x. Cos 2x, you want to make it 2 sine squared x. Or solve this, sorry. So we got to convert this probably into this thing right here, right? So cos 2x is going to be cos squared x minus sine squared x, and that's going to equal 2 sine squared x. Okay, so now we have cos squared x is equal to 3 sine squared x, right? We can now finish it off even more. How would we combine these? Think about how we could combine these, right? So we want to combine these. Think about putting sine over cos or cos over sine. Sine over cos is a little bit easier, right? So bring it through, you're going to have 1/3 is equal to sine squared x over cos squared x, which is tan squared x, right? So if you want just tan x, you take the square root, and it's 1 over root 3. And all of a sudden, we end up in a situation that we know that we can solve. Because if you look at a 30-degree angle, it's 1, 2, root 3, and this will indeed be 1 over root 3. So x in this case is 30 degrees, or pi over 6. And it's also going to occur all sine tan down here. So at 1 or at 2 tan, or 7 pi over 6. And then you can give me a general solution that it occurs at pi over 6 plus pi n, where n is an integer, because it occurs every pi now. All right? So that's a funky question. There's a lot of things involved. But, again, a lot of it's algebra. Hopefully you can make some sense out of it. Simplify these. Okay, simplify these. Well, let me bring our double angle identities down, make it easier for us to work. We have them right in front of us. So let's look at this. 12 sine 4x cos 4x. 2 sine x cos x. So these are your theta. I need a 2 in front. Well, I got a 12 in front. How do I get a 2 in front? Right? How do I make this a 2 in front of this? Hopefully you can see that if you took a 6 out, you'll be left with a 2. So now 2 sine x cos x is sine 2x. So this is going to be, right, sine of 2 times 4x, which is equal to 6 sine 8x. Okay, so again, see that you need the 2 in front, so we factored out a 2. Left with 6 times 2 is 12, right? So now sine 4x cos 4x, this is like your theta. So 2 sine theta cos theta is sine 2 theta. So sine 2 of your theta, which is 4x, boom, 8x. Yes, funky. Why, Mr. Gregor, why? All right, 8 cos squared times, or 8 cos squared 6x minus 4. Well, if I want to simplify this, I'm looking over here somewhere. Look at this. 2 cos x minus 1. 2 cos x minus 1, 6. I think I can make that work. I can think about factoring something else out again. How could I make that 4 into a 1? If I factor a 4 out, you're left with 2 cos squared 6x minus 1. Now, you're looking pretty much like this bad boy right here. Okay? So, 2 cos squared, this is your theta. So this is equal to cos 2 times 6x, or 4 cos 12x. And you've simplified it down to the bare bones, all right? Prove this. I don't want to prove this. I sure hope I don't get this wrong. Let's give it a shot. So sine 6x. Let's break that into 3x and 3x. So I don't know if this is the right way to go, but that's going to be 2 sine 3x cos 3x, right? Because that's like 2 times 3x here. That's like 2 times 3x. So it's 2 sine 3x cos 3x, okay? Now 1 plus cos 6x. I got a 1 in here. Talked about some strategies. Now we got strategies when we're dealing with these ones, because 1s can cancel out if you use the appropriate thing, right? Now I can see that cos 2 theta can be a variety of these different ones. But if I change cos 6x into this, I'm still going to have a 1. But then I might be able to make something work with that. But I'm kind of looking at here, because I think this might work a little bit better, right? So, because it's going to get rid of the 1. So let's just try it. So 1 plus. So cos 6x is the same as saying cos of 2 times 3x. So that's going to be 2 cos 3x minus 1. And sure enough, look, the 1's cancel, right? The 2's cancel. The cos 3x cancels. And you end up with this is a cos squared 3x. So you end up with a sine 3x over a cos 3x, which gives you a tan 3x, and you're done. Okay, which is your right side. So what I missed here was this was a cos squared. My apologies. So the cos 3x takes one of the cos x's. You're left with the cos x. Boom, there you go. All right. So yeah, you're watching me work through these. You're watching me solve these, but that's kind of the idea. Show you that they are manageable. I'm going to make mistakes. I'm going to go down the wrong path at times. You just got to do what you can, right? So, tan 2x. Oh my goodness, I don't have tan 2x on here. Do I have it? Did I give it to you up here? Oh, I got it up here. Oh, I didn't put tan 2x on the sheet. Okay, I'll fix that. We have it up here though. Okay, we have it up here. So I'm going to write down this right now with an x up there. Okay, so that's going to be tan, so it's going to be 2 tan x over 1 minus tan squared x. Now we have to look at this, right? In the third quadrant, sine is opposite over hypotenuse, so that's 12, that's 13, that's going to be 5 if you use Pythagoras, right? So this is my x value. So now, that's a minus 5, 2. So tan x is minus 12 over minus 5. So it's going to be 2 times 12/5, positive because it's a minus over minus. All sign is positive. And then 1 minus tan squared x, which is 12 over 5 squared. Okay, now what do we have here? We have 24 over 5. This becomes 1 minus 144 over 25. That's 25 over 25. 25 minus 144, what is that? 119. So over negative 119 over 25, right? That's crazy. So this is going to be times negative 25 over 119. That goes into there 5 times. 5 times 24 is 120 over 119 negative, and I think that's actually the answer. That is a bit outrageous, but hopefully we can still make some sense of it. It is indeed taxing dealing with fractions. I'm sure Luke's going to find out that I made a mistake. Hi, Luke. Find out where I made a mistake. And that is that. Now, those are a few examples, but there is something else that I'd like to show you, and we can see where these come from. These prove to be useful when we want to get rid of a cos squared or a sine squared or a tan squared. And what it is, it's using these 3 identities here and rearranging them, right? So if you look at cos 2x here, cos 2x is equal to 1 minus 2 sine squared theta, okay? That's one of our definitions. Actually, I've got them right here, so I don't even need those. What we have here is cos 2x. This is an identity, right, that we just gave you. Now, if you rearrange it to solve for sine squared, you bring the 1 over, or bring that over here, it becomes positive. You rearrange it, we end up with this, okay? Now, notice that you can also write it as 1/2 1 minus cos 2x. But what you've done is you've given a squared or a quadratic trig function, you know, if to second degree, you've reduced it to a cos 2x, and then we can deal with it from there maybe in an easier manner. Similarly with the cos squared x and with tan squared x, using the identity that tan is equal to sine over cos. These are what we call power reducing identities. I'll probably end up making another video with a few more examples, but that should probably do you for now, ladies and gentlemen. You know the work in the book, give it a shot. Come on Monday with some questions.